Hello. Modeling RLC circuit with second order ordinary differential equation. So RLC circuit is an electrical engineering application for differential equations. So basically it is the application of the Kirchhoff's first law. Kirchhoff's voltage law. Voltage law, which states that the voltage in an RLC circuit is the sum of the voltages across the capacitor, the resistor, and the inductor. So the RLC circuit is represented like this. So capacitance is represented like this. The inductor is represented like this, and the resistance is represented like this. And then this the sum of the voltages across these is equal to the the voltage applied across the inductor. Okay, so there is this applied voltage over here, which is represented by E of t that we need to determine. And normally this E of t is taken as E naught sine omega t, where omega is the frequency of this of the current passing over here. So this is the resistor, this is the capacitor, and this is the inductor. Okay, so if we understand these their relationships, then it is easy to draw this ordinary differential equation. So according to the Kirchhoff's voltage law, so voltage across the resistor VR plus voltage across the capacitor VC plus voltage across the inductor VL will be equal to this E of t, the voltage. So this E of t is called as the electromotive force. Electromotive force, just like the driving force in the spring mass system, EMF. Okay, so voltage across the resistor is actually given by VR is given by the resistance times the current. So voltage is measured in volts. Okay, so this is the voltage, which is actually the potential difference. Okay, voltage or the potential difference is measured in volts. R is the resistance, which is measured in ohm units, and I is the current, which is measured in the amperes. So voltage across the resistor is given by this relationship, P is R is equal to Ri, and the voltage across the inductor VL is given by this relationships, L times the di over dt. Di over dt is the change of current, okay, with respect to time. Okay, rate of change of current with respect to time times the L. So where L is the inductance, L is called as the inductance, and this is measured in units which are called as the Henry. Okay, and the voltage across the capacitor is given by this relationship, charge over capacitance. So where Q is the charge, okay, equal the charge, and it is measured in coulombs. Charge is measured in coulombs, and charge is actually the current times the time. Okay, current times the time. So charge is basically the total current passed in some time, and C is the capacitance. Okay, C is the capacitance, and the capacitance is measured in farads. Okay, farad, so its units are farad. So if we want to apply this all these relationships in over here, so maybe I can put it in the into this equation. So VR was Ri, and then plus VC was Q over C, and then VL was L di over dt, and that is equal to the electromotive force, which will be represented by E naught sine omega t. Okay. So to further convert this equation into some differential format, so what we can do is we can change these units to either represent the dependent variable to be either I or Q. So let's change it to I. Okay, first. Okay, Ri. So this is there already. So Q is equal to I times T. So this is C, and then L is equal to di over dt. So it is equal to E naught sine omega t. If we differentiate this equation with respect to t, okay, if you take a derivative of this equation, then this will be the Ri prime, and then this will be the this equation will be then I over C. Okay, and sorry, this term will be, because the derivative of t will be 1, di over dt will be 1. Okay, and then it will be L di square d2i over dt square, and then over here it will be because it is sine, so it will be E naught omega cosine of omega t, and then it will be divided by okay, so we will rearrange the terms and write it a little bit nicely. So it will be L d2i over dt square, so it will be L I double prime, and then R will be then I prime. Yes, and Ri prime, then we have this 1 over C times I. Okay, and then it equal to E naught omega cosine of omega t. Okay, so this will be the differential equation for the RLC circuit in terms of the current. Okay, so it is in terms of the current. If we want to represent this equation in terms of the charge, so we can also represent it. So for example, we know that the current is equal to the charge divided by time. Okay, charge divided by time. Okay, so if we represent, if we, for example, take this original equation over here, okay, and in this original equation, okay, so for example, this in this equation, I represent I with Q over T. Okay, R is equal to Q over T, and then Q over C is already there, and then this is plus L. It is L di over dt, so it is the change, so it will be the second derivative of the current. Okay, di, then it will be d2 it will be the second derivative of q, and then it will be E naught sine omega t. Okay, so in the charge form, this equation will be LQ double prime plus RQ over T. So RQ over T is can be represented as dq, okay, over dt. So q prime and plus 1 over c q, 1 over c q is equal to E naught sine omega t. So one of these two forms of the terms can be used. Okay, so if, for example, if I compare this or this equation with the mass spring equation for the forced driven cases, then we have this equation m y double prime plus k y prime plus sorry, this is not k, this was c. So this was c, and then plus k y, that it was equal to f naught cosine of omega t. So if I compare this equation with this current equation, so you can see that mathematically both equations are same. Okay, only thing is that the mass is replaced by the resistance. This equation, only thing is that the mass is replaced by the inductance, the resistance is replaced by the damping force, and the capacitance is replaced by the mass spring constant. Okay, and all the other terms are having the same meaning. Okay, so both equations are mathematically similar in meaning. So we'll see one example now. Okay, let's do one numerical problem. So this is the statement of the problem. Example. The current. So we need to find the current. That means the solution of the equation, differential equation, in an RLC circuit with R is equal to 11 ohm. This is the symbol for ohm. L is equal to 0.1 Henry. The capacitance is 10 power minus 2 farad, and which is to connected an EMF which is E of t is given as this. So we can take this second value. Both values are equal. 60 times 2 pi t is 377. So 110 sine 377 t. So first of all, first is the capacitance inductance. Okay, so 0 in the if we write the equation, so inductance comes first, 0.1. It will be I double prime d2i over dt square, and plus resistance I prime, and plus capacitance. So it is 10 to the power minus 2, it is 0.001. It is in the equation, it is 1 over c, so it should be 1 over 10 power 2. It should be 10 to the power 2. So I should write it like 100 I. Okay, and that is equal to 110 sine 370. So we will complete this in the next video clip.